This lesson is on bond polarity and dipole moments. So we just finished up the majority of the information in Chapter 8, chemical bonding, and this is a combined chapter, Chapter 8 and Chapter 9. So we're beginning topics from Chapter 9 today. So in Chapter 8, we discussed bond dipoles. But just because a molecule possesses polar bonds does not mean the molecule as a whole will be polar. By adding the individual bond dipoles, one can determine the overall dipole moment for the molecule. Now, the way you decide how to write the dipole or to represent the dipole is with a vector. A vector is essentially an arrow with a plus sign on one end of it and the arrow pointing in the direction towards your more electronegative element. So when you draw your Lewis structures, to determine how or where to draw your vectors, you will use your electronegativity table. You will draw the vector, as we see here with the carbon dioxide. They drew the vector towards the oxygen from the carbon, and then for this bond, from the carbon towards that oxygen. These are two vectors in opposite directions. So this represents the situation where the vectors cancel out. Vectors have both magnitude and direction. So when you have your vectors, let's say if this vector, since they're identical bonds, if this vector, we'll say it's a magnitude of 1 unit. I'm just coming up with that for an example. That means this vector also, because they're identical vectors, will be 1 unit. Now normally, when you would say 1 plus 1, it would equal 2, because there are two vectors there. But the direction of the vector makes all the difference. When the direction is exactly opposite, the vectors actually cancel. So if you could take this vector and pick it up and superimpose it, we'll say on top of the other vector, you'd have two identical vectors going in opposite directions. So the vectors actually cancel out. So this is an example where you have cancellation of vectors and you would have no dipole moment. So carbon dioxide, his vectors actually cancel out. So this molecule does not have a dipole moment. Now, if you think about a water molecule that I have here, water is a bent molecule. So anytime you have vectors at angles, as we see here, the hydrogen is the least electronegative element, and your arrow always points towards your more electronegative element. So here, this vector would go up. So they're at an angle. So when your vectors are at angles, you actually have to take the average of that to get the overall dipole moment. And the average is going to be exactly in the middle, going in the same direction. So normally, when I'm representing the average of the vectors, I will draw that with a dashed line. So this vector here, I would have drawn as a dashed line going up. And that represents the average of these two. So it's kind of like these two get averaged, so you pretend that they're not there. And this is your overall vector. There's a net vector left over. And anytime there's a net vector left over, you would say that the molecule does in fact have a dipole moment. Let's consider a molecule of hydrogen chloride, HCl. When you place the hydrogen chloride in an electric field, the molecule has what we call a preferential orientation. What that means is it has a center of positive charge and it has a center of negative charge. So the molecule is considered to be dipolar, or you would say it has a dipole moment. So here I have 3 molecules of hydrogen chloride. Notice my vector, I draw the vector towards the chlorine, indicating that the chlorine is more electronegative and is pulling those electrons towards it. So the electron density would be towards the chlorine. And these red arrows here represent the electric field. Notice that the preferential orientation will have your less electronegative element. It gets what we call a partially positive charge. And then the more electronegative element, in this case the chlorine, has a partially negative charge. So in an electric field, the partially negative pole or part of the atom would be lined up towards the positive electric field, and the hydrogen, which is a partially positive, would be oriented towards the negative electric field. Now I'm going to show you for just a minute. I'm going to, in just a second, we'll back out and we'll look at the PhET simulator to kind of make that a little more visual for you. So we use vectors to represent a polar bond. Anytime you have a vector, the partially positive end is going to be near the end of the vector that looks like a plus. And the partially negative atom will be the atom that is more electronegative and is pulling the electrons towards it. Any two-atom molecule that has a polar bond, so when you do your delta X calculation, if you get a delta X or electronegativity difference between 0.5 and 1.6, it will show a dipole moment. So you would draw the vector. There's your HCl again. If there's just a two-atom molecule, that is your vector. There is no vector to cancel with it. So it will, in fact, have a preferential orientation in an electric field, and therefore it has a dipole moment. There are also some polyatomic molecules that exhibit dipolar behavior. So the question becomes, how do we know when they exhibit dipolar behavior? Well, it's when the vectors do not cancel out, like with the water example a while ago. When the vectors are coming at angles instead of exactly opposite, then you have to take their average. So the average of those two vectors would be, as I said earlier, here in the middle. So you would kind of pretend those are not there anymore because you average them, and this is your average. There is not another vector that will be canceling it out. So the water molecule will also have a dipole moment. Some molecules that have polar bonds do not have dipole moments. Again, how do we know? Well, that's when the bond polarities, or the vectors, are arranged so they do exactly cancel each other out. As with the example I used earlier, the carbon dioxide. Notice you have two identical vectors, but they're pointing in opposite directions. So these two cancel out because they're equal and opposite in direction. So they actually cancel, and you would say there's no net vector left over, so it does not have a dipole moment. Now, on the off chance when you draw your vectors, for example, this can happen with hydrogen cyanide. When you draw your vectors on hydrogen cyanide, if you look at your electronegativity chart, you would draw one. This vector would be for the HC bond. It would point towards carbon because carbon is more electronegative than hydrogen. And then if you compare the electronegativities of the carbon and nitrogen, you would draw the vector towards the nitrogen. So notice here we have two vectors that are going in the same direction. So you add the vectors. So you do have a net vector. The net vector would be this. And so that would have a dipole moment. So it would have a dipole moment in this case. I'll put DM for dipole moment. So in this case, the vectors cancel. So if they cancel, the molecule would have no dipole moment. But if the vectors add together, you would say it has a dipole moment. Now, before we do some examples here, I want to move over to the PhET simulator, and let's take a look at that for just a second. Let's give this 1 second to clear out of the way. So here, this represents a two-atom molecule, and right now I have them having the equal electronegativity. So if the atoms are exactly the same, if the atoms have a delta X less than 0.5, you would not draw a vector. So here, you would not draw a vector on this, and you would say, no, it does not have a dipole moment because it's a nonpolar bond. But let's say if I slide this over and make element atom B be more electronegative, notice what happens up here with my vector. So I notice how the vector gets larger as I move it over and smaller as I move it back. So as you get a more electronegative element, there is a greater pull on the electrons. So the electron density would go towards the more electronegative element. Now I'm going to show the partial charges. And I'm going to also show the bond character. Notice here this is more ionic because of that great vector. Now, let's look at the electron density. Notice how it's darker here. The electrons are being pulled towards this more electronegative element. Now, here's where the electric field comes in. I'm going to turn the electric field on. Now, watch this. There's my partially positive field, and here's my partially negative. Look what happens when I try to turn that. If I try to turn that and make it rotate this direction, as soon as I release it, it has that preferential orientation moving back. Negative, partial negative attracted to the positive, and the partially positive attracted to the negative. Now let's look at a 3-atom molecule. Let's turn our electric field on, and let's show our bond dipoles. They're going to show up in black, and the molecular dipole, which would be referring to the molecule's dipole, will be showing in yellow. That's where we kind of see where they cancel or not. I'm also going to indicate the partial charges. So I'm going to put element B as a very weakly electronegative element. And I'm going to put atom A as a more electronegative. I'm going to actually make A and C be exactly the same electronegativity. Okay. Now notice what happens when they're exactly the same electronegativity. There is no preferential orientation because these dipoles are equal and opposite in direction. And so therefore, it doesn't orient in the magnetic field. It does not have a dipole moment. Notice if I were to bend it and make it bend, you see that as the dipoles are at an angle, the vectors are at an angle, you see how that average there is pointing in the same direction as the two dipoles, but it kind of has an additive effect. But as they get exactly far apart like this, there's not really a preferential orientation. Now, let me move this in some. Now, and I'll move this in some as well. Notice when the vectors are equal and opposite, and I sort of turn that around. And this does not let me show when there's lone pairs, y'all, but if it were bent, notice if it were bent, it would have a preferential orientation because you have that net vector here, and your partial positive would be towards your negative, and your partial negative poles would be towards your positive. So again, that's that preferential orientation. All right, let's go back to the notes, and let's look at some examples. All right, so if we're going to look at some Lewis structures here, carbon dioxide. So I'm going to go ahead and just sketch those out. Carbon dioxide's Lewis structure would like, I'm sorry, I jumped the gun on that. Let me change that. This is carbon monoxide, so let me go back. So carbon has 4 valence electrons and oxygen has 6. It gives you 10 total electrons. So you would say C-O. So as you draw your Lewis structure, we've used 2 electrons here. So 10 minus 2 gives you 8 electrons we're still going to use. So we would put 2, 4, 6, 8. And here you got to borrow and share. So you're going to swing a pair down. You're going to swing a pair up. So that's going to give you C triple bond O, and then you would have your Lewis structure there. That is the completed Lewis structure. So let's take a look then at how you would draw the vector there. You would draw the vector towards your more electronegative element. There's only one vector, so you would say that does have a dipole moment. And that's because the vector doesn't have another vector to cancel with it. All right, let's look at the next one. All right, the next one is diatomic chlorine. If you draw the diatomic chlorine, you add up your valence electrons. There are 14 total, and you end up with Cl-Cl. Now, as you distribute all of your electrons, I said there were 14 total, you end up with a single bond on your structure, and it's just a linear molecule. Now, you cannot draw a vector here. Why? Well, both of these are identical atoms. So this is a non-polar covalent bond, so therefore there's no vectors. So don't get sucked in and tricked thinking you always draw your vector. You can only draw a vector if your delta X is 0.5 or higher. Okay? All right, SO3. So we have 6 plus 3 times 6 for our valence electrons. That's going to give you 6 plus 18, which is 24 electrons. So we're going to put our sulfur and then attach the 3 oxygens. All right. I'll try to erase some of these. All right, so let's figure out how many electrons we've used so far. So far, we have used 2, 4, 6 electrons. So, minus 6, that means we have 18 lone pairs to place. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So we run out of electrons. We've used all 18. Now check for your octet rule. All the oxygens are good, but sulfur is not. So this is, again, where you have to borrow and share. Now, what kind of structure is this that we just learned about? Hopefully you realize there's actually 3 equivalent structures here. In other words, this oxygen can share, this oxygen could share, or this oxygen can share. So this is a resonance structure. So I'm going to go ahead and draw them all just for practice. So the 3 resonance structures you would want to draw would, if you take the lone pair from this oxygen, okay, you would just swing it up. And so that would give you an S with the single bonds here and here, the remaining electrons. Okay, and that would give sulfur 2, 4, 6, 8. Another equivalent structure, again, if you have 3 resonance structures, you represent resonance with the double-headed arrows here, pointing towards one another. So we could have borrowed the oxygens, the double bond or the lone pairs from the bottom oxygen, so that would have been there. And then your structure would look like this. Again, that is that resonating double bond here. And then finally, you could have borrowed it from this one. So I'm going to go ahead and erase this original here and finish that up. So your other resonance structure, because there's 3 total, would have the double bond on the right-hand side. Okay, so there's 3 resonance structures. So I wanted to review resonance. Now let's get back to the polarity. So if you look at this, you see that this would be considered a trigonal planar molecule. All the bond angles are 120 degrees. Now think about what that looks like. So with a trigonal planar, your central atom has evenly distributed 3 other atoms around it. So let's just think about the trigonal planar in general. So when you draw your vectors have to mirror the shape of the molecule. Now, the arrows are going to point towards the oxygens because there's more electronegative. So you'll have one vector going from the sulfur up to the oxygen here, one going here, and then one going here in this direction. So those are your 3 vectors. You have 3 vectors that we're drawing here. In this instance, you have vectors at angles. So anytime they're at an angle, you have to take their average. So I'm going to just take the average of these 2 first. If I average these 2, then the average would be down here, pointing in that direction. So I'm going to scribble that out. And so that leaves me with this vector and this vector. Notice they're equal magnitude, opposite direction. That means they cancel. So those vectors cancel. So the vectors here cancel. And so you would tell me that this does not have a dipole moment because the vectors cancel. All right, let's take a look at the methane. So carbon has 4 valence electrons and the hydrogens have 1 apiece, but there are 4 hydrogens here. So that gives us a total of 8 electrons that are going to be used to bond with here. So carbon goes in the middle and you put your 4 hydrogens around it. That's 2, 4, 6, 8, and that is your Lewis structure. Okay, so this is tetrahedral. Now, when you draw your vectors, it's based on the shape of a tetrahedral molecule. Remember, tetrahedral looks like a little tripod. So when you draw your vectors, the vectors are going to be like the little tripod as well. So the vectors are going to point towards the carbon. Okay, so now these are at an angle, these two are at an angle, so I'm going to take their average. That means their average is right here, right in the middle here. So I'm going to scribble that out and scribble that out. So this is one of my averages here. And then these two are at an angle, so I'm going to take their average. It goes right here up in that diagonal. So scribble that out and scribble that out. Now, at this point, you have those two averages, and notice how they're equal but opposite. Therefore, vectors cancel. So this has no dipole moment. All right, let's look at the H2S. H2S, if you draw that Lewis structure, you would have, and I'm going to go ahead and draw it bent because this is going to end up being bent. The sulfur has hydrogens, and you got your lone pair here and here. So since it's a bent molecule or angular, the vectors are going to point towards your more electronegative sulfur. So point them up, point them up. So now we have two vectors at an angle. So anytime the vectors are at an angle, you're going to take the average of the angled vectors. So there's your average. And anytime you take an average, you kind of erase the original. So I scribble them out. That leaves me with a net vector pointing upwards. That is my net vector. There is nothing to cancel with it. So this does have a dipole moment because you have one vector left over. All right. Now, let's do these. If you would just pause the video and you try these on your own and then check your answers when you're done. Resume the video. So, all right. I'm going to continue on, assuming you've paused and you've tried them on your own. So for this one, we just did this one actually. So the H2S, we already said it has a dipole moment because when you drew your vectors, they were pointing at an angle. And since we just drew this one, I'm not going to redraw it. So your average went upwards. You scribble these two out, and that leaves you with a net vector. So it had a dipole moment. All right, let's go to your NH3. If you look at your ammonia and you draw your ammonia structure, you should have drawn nitrogen. There should have been a lone pair on the top of the nitrogen, and you should have your three hydrogens around it. This is trigonal, pyramidal. And so this is at a little pyramid. So when you draw your vectors, the vectors are going to be looking kind of like a pyramid shape. Okay. Got that stray mark there I want to erase. Okay. So they're kind of a little pyramid shape. There's my vectors. So we're going to start taking some averages here, y'all, because they're at an angle. So I'm going to start with these two. The average of those two would be right there between them. So scribble that out and scribble that out. When you scribble them out, y'all, you have to block them out. You consider they're no longer there. Now, I've got this red average vector and then the original blue vector. I have to average those two. So I'm going to average that with a different color just to make it hopefully where it'll be easier for you to see. So if I average these two, it's going to be right here in the middle of those. So if I average them, you scribble that out and you scribble that out. So I've not scribbled out that. That is the last vector. If there's one vector left standing, like we have here, you would have a dipole moment. So yes, the NH3 has a dipole moment because you have a vector left over. CF4. If you draw your Lewis structure for CF4, you have your carbon in the middle and you have your four fluorines around it. So we can already tell this is going to be tetrahedral. Don't forget to put all your lone pairs. is tetrahedral. And so when you draw the vectors on a tetrahedral, remember, you have them all at angles. So they're going to point towards the fluorine. You'd have one pointing that direction, one pointing that direction because you got your tripod, one pointing that direction, and one pointing that direction, all pointing in the tetrahedral little tripod shape. So let's do our averages. Since all these are at angles, we have to do the average. So I'm going to do the average of these two. You'd have one net vector pointing in that direction. So scribble out that one and scribble out that one. These are also at an angle, so do your average here. Scribble out that one and scribble out that one. So these are our two averages that we've not done anything with those yet. So let's kind of look at those and see. Notice these are equal but opposite in direction. What that means is they cancel out. So all the vectors cancel. So you would say that the CF4 does not have a dipole moment. So no dipole moment. For oxygen, hopefully you can look at that and tell that's going to be a nonpolar covalent molecule. The Lewis structure would have not a triple bond, sorry, I jumped the gun on that. The Lewis structure would have a double bond if you draw its Lewis structure. But since we're talking about dipole moments here, you're not going to have a vector to draw because this is a nonpolar covalent bond. So there's no vector, so there's no dipole moment with that one either because there's not a vector you can draw. BH3, boron trihydride. This is going to be a trigonal planar structure. 2, 4, 6 electrons is all you got. This is trigonal planar. Since it's trigonal planar, you're going to draw your vectors based on that particular shape. So these two are at angles. I would point the vector towards the hydrogen. He's the more electronegative element here between him and boron. And there your vector's going to be down there. So you have three vectors in a trigonal planar arrangement. Now, when they're at angles, remember you take their averages. So I'm going to average these two first. So that average will go straight up there. Scribble that one out and scribble that one out. And so now I have this one and the original vector there. Notice they're equal magnitude, opposite direction. So the vectors cancel, so it has no dipole moment. Again, vectors cancel. And that's for the boron trihydride one. Now the last one, NF, if you add up your electrons, you have 7 from the fluorine plus 5 from the nitrogen. That's 12 total electrons. So you're going to N-F. I'm going to do a little erasing here on this one just so I have some room. So we had 12 total electrons. We've used 2 of the 12. All right, so 2, 4, 6, 8, 10. 2, 4, 6, 8, 10, 12. I've used 12 electrons. So now I've got to share to make sure everybody has their octet. So I'm going to have nitrogen to swing a pair down to the fluorine. You have a double bond. N, double bond F. Two, 4, 6, 8, 10, 12. That's 12 electrons. Now, with this one, it's a linear molecule, so linear. We are going to draw a vector here because nitrogen and fluorine do not have the same electronegativity, so the vector is going to point towards the nitrogen. There's not another vector to average with it or to cancel with it. So yes, this will have a dipole moment because you have one net vector left over. So this has been our lesson on dipole moments, and we will talk about these more in class.